Hi, my name is Kobe Bui, and this is my tutorial on how to implement the data structure called tries. So tries are a tree-based data structure used to store associative arrays. The keys for the nodes of the tree are typically used as strings, and it's usually implemented in the form of a dictionary. They're very good for efficient retrieval and storage of keys, and they're very space efficient, and so they're good for large data sets. The way it's implemented is it starts as a tree with a root node, and within that node, it contains an array where each index is associated with a certain character. And it also contains a Boolean value that marks it as the end of a key. So in this scenario, which will be shown, it's to mark the end of a word. Functions that this data type supports are insert, delete, search, and prefix search. So to begin with key insertion, you would input your key in this scenario, it'd be a string, and it has a time complexity of O of n, where n is the length of the string, and so it only takes one step per character in the string. And so what you do is you start with your root node, and based off of the first character in the string, you would create a new node at the in the array at the index which would correspond. And so we'd create a new node for C at the third index of the array because C is the third letter of the alphabet. We would then traverse to that C node and then move to the next letter of the string, which in this case is an A. And so same thing where we create a new node at the corresponding index in the array, which in this case is the first index, and then traverse to that node up until we get to the last letter in the string. Um, in which case, once we reach the end, we change the condition for is word end from false to true, so that when we access the try later, we know that cat is a full word. And then building off of this, if you were to insert another word in this scenario, car, you would start at the root and then go through each letter of the string, checking to see if there exists a node for its corresponding letter in the in each trinode. And if it does, you just traverse to it, and then once we get to an A, it doesn't have a corresponding node for R yet, so we would create that node and then traverse to it and then set is word end to true. The next commonly used function for tries is key search, where we're searching to see if a word exists within our dictionary or a key exists within the try. And so, going off of the try that we had originally, we're going to search for the word car. So we would start from the root and then traverse through each letter. And so, as long as each node has a corresponding node in its associated array that points to the next letter, then we just continue moving on. And once we reach the end of our input key, and the condition of is word end is equal to true, then we would return true. Um, then another scenario is if we were to search the word can, we traverse to A again, but in this scenario, the index for n in the A node which would be the 13th index, is a null pointer, so we would return false. The next function used in tries is prefix search. And so the only difference between key search and prefix search is we don't require the condition of is word end to be true. And so let's say we're searching for the prefix of CA within cat and car, which is what we already have in this dictionary. As long as we can to um, traverse to A, and so as long as C has a node set for the index of A in its array, then we can return true. But if we were to search up CB and it has a null pointer for B in the array that belongs to C, then we'd return false. And the last function is key deletion, um, where we delete the a word from our dictionary, basically. And so in this scenario where we have the word cat, car, and cars inserted, we want to delete car from our list of viable words. And so we traverse through the trie until we reach the last letter and change the condition of is word end from true to false. And so now when we search for car later and car is deleted, since is word end is equal to false, we'll return false for the search function. And then if we wanted to delete the word cars, we do the same thing where we traverse to the last letter. And then because the node for S has no children node, we're able to delete it and then move back. And um, so the delete function is recursive. And so as we traverse through, once we reach the end and we perform our deletion, we move back to the previous um, character in the string. Because R now has no children after the deletion, we would also delete R and then move back to A. And because A has a child of T, um, we wouldn't delete A and we just traverse back up to the root. All right, so I have an implemented version of the try started here in code, and we can we'll just begin with the class structure for try node. And so we have, of course, our constructors, destructors, and member functions. But if we go down here to our so our private members, we have the associative array and our conditional for if the node is a word end. And you'll see in this scenario, I have a node size of 52 as opposed to 26, and that's just because I implemented the try node to be able to also handle uppercase characters as well as lowercase characters. And then just some overloaded operators. Um, Screen's moving really slowly, but bracket operator just so that we can access the child node um, with an inputted character more easily from our functions, and then a comparator operator to see if our node is equal to another node value. And then as well as an is empty function to see it basically just iterates through the array of whatever node it's on and checks that every value in the array is equal to null pointer. Otherwise, it returns false. And so to begin with our insert function, it inputs a string value, and then um, for every character in the string, um, we go through, and if the current node that we're at doesn't have a pointer pointing to the character, pointing to the next character, then we create a new one for it and then traverse to it and continue through that loop until we get to the end of the word. And once we reach the end of the word, um, we set the is word end value from false to true if it isn't already set. So just a demonstration of program working. So we set insert to our function, and then we want to insert car. So now car is inserted, and I'll get to the search implementation in a second. But if we search for car, car is now found within our data structure. Next is the search key function, which also inputs a string and it traverses through each character of our string until it reaches the end, um, with the condition that if whatever node it's at, if the next one doesn't have a character in its member array, then we return false because if it doesn't have the next letter within the middle of the word, then it won't have the rest of the word. And so we return false. And then additionally, if we do reach the end of the word and the is word end value is set to false, we'd return false. Otherwise, we return true. So let's say we had the word cat and the word cater. If we delete cat, and so only cater exists in the dictionary, but we search for cat because it won't have a is word end value of true at the letter T, it would return false for our search function. Same thing with our search prefix function. It looks very similar, except the end section is removed because we don't need a check for the is word end marker. So as long as we're able to make it through the entire string that is our prefix, then we return true. And then lastly, our delete key function, a little more complicated than the rest of them, but we have a helper function here which inputs the current our current index within our string. So basically just whatever letter we're at, this just marks it here. And we go through and we check if if the current letter that we're at in our string is the end of the string. And then if not, we just recursively loop through our function until we reach the end. And then once the end is reached, if um, we check if the is word end value is true. If it is true, we set it to, oh, actually, no, we just set it to false regardless. And then we check if the end character node is empty. So if the node doesn't have any children nodes, then we're free to delete it. Otherwise, we just loop through the end of the function and then recur back to here. And then we just continue to check if our child node is empty. And as long as it's empty, we can delete and delete until we reach a node that isn't empty. And then we just traverse back up. And so just a demonstration of all of our functions working. We already showed insert, but so let's say we insert car. We will insert cars, insert cat. Um, and so now if we were to search for cat, cat is found. If we were to search for car, car is also found. Now, if we try to search for a word that we haven't inputted, like can is not found. Um, and a demonstration of prefix search. We search for the prefix CA. CA is found. We search for CB. CB is not found. And so now we have the words car, cars, and cats, I believe. And so if we were to remove the word car from our dictionary, um, so now that just leaves us with cat and cars. And I were to search for the word car, car would not be found. Um, but car is still there. And if we do a prefix search, because now we're not checking for that end of the word value. If we search for car as a prefix, car still exists. And then if we delete cars, search for cars, cars is no longer found. Search for cat, cat is found. Um, and that's a demonstration of a try and practice. Obviously, the data set would be a lot larger than just a couple of words, but you could just have an input file and just loop through a whole bunch of words and input an entire dictionary into this data set. And it'd be a really efficient way of traversing to check if words exist, if words don't exist, see if you're spelling something right or not, or lots of other implementations. Yeah. Thank you for watching.